Okay, so we're going to go ahead and continue with the solubility rules. Last time we had just gotten through the halides. Now it's time to start with the sulfates. Then we'll move on to the things that are usually insoluble. Sulfate, hopefully you'll remember, is SO4 2-. So any salt involving a positive ion, a cation, bound to SO4 2- is called a sulfate. Okay. So sulfates are usually soluble. The exceptions are, again, silver, lead, and mercury 1. But also, as you see here in the list, calcium, strontium, and barium. Those are alkaline earth metals. They are the ones down toward the bottom. Calcium, strontium, barium. So if you're very visual, maybe that'll help you somehow. I don't know. But calcium, strontium, and barium, calcium 2+, strontium 2+, barium 2+, are generally insoluble sulfates. So calcium sulfate, strontium sulfate, barium sulfate, insoluble. Silver sulfate, lead 2 sulfate, mercury 1 sulfate, also insoluble. So you see that these three are harder to get to dissolve because they take things that are usually soluble and make them insoluble. These three are less restrictive. You mix them with halides, they'll still dissolve, but not with sulfates. Sulfates are easier to pull out of solution. Next up, we have things that are generally insoluble. Carbonate, phosphate, chromate, and sulfide. That's probably going to mess you up, but hopefully not too badly. Carbonate, phosphate, chromate, and sulfides. Do not confuse sulfides with sulfates. Those are not the same thing. All right, these are generally insoluble unless you mix them with something that is always soluble. So you have our alkali and our NH4+. See, these guys are always soluble. Their solubility trumps insolubility. Okay. Next up, we have hydroxide, OH-. It's always insoluble, except with these guys or barium. Okay. Now, barium hydroxide, that's BaOH2. It's not hugely soluble, but it's soluble enough that we sort of kind of just a little bit treat it as soluble. Okay. These guys, always soluble, and their solubility wins when you compare them, bond them, mix them with these guys. Okay. But carbonate, phosphate, chromate, sulfide, and hydroxide are all insoluble most of the time. We've already talked about this a little bit, but we are going to go ahead and clarify it. Okay. Molecular and ionic and net ionic equations. It's a way of only including what really matters in our chemical equation. So going back to silver nitrate, aqueous, plus sodium chloride, aqueous, you mix together and you get silver chloride solid and sodium nitrate aqueous. Okay, so this is the molecular equation, all one word. Now, we use that name even though none of these is a molecule. A molecule refers to covalent compounds. None of these are covalent compounds, so it doesn't really count. But we call it the molecular equation just because we're writing them as if they were bound together. But if they're aqueous, they're not bound together. So what we do next is we write out the ionic equation, in which we take every single aqueous compound and we break it apart into its ions. So silver 1+ aqueous plus nitrate 1- aqueous plus sodium 1 plus aqueous plus chloride aqueous goes to form silver chloride solid. It's solid, we don't break it apart. Plus sodium 1 plus NO3 1 minus, both aqueous. Now, having written out the full ionic equation in this way, we can identify things that are the same on both sides of the reaction. They haven't changed. So they're not participating. They are spectator ions. Okay? They like to watch. They're not doing anything. They're not taking part in the reaction, so they might as well not be there. So what we do, moving on from the ionic equation, is we write the net ionic equation. Okay? That's where you remove the spectator ions and only, oopsie, I made a mistake up here. I'm terribly sorry. Okay? The reason I'm calling it a mistake is because chloride does participate in the reaction. What doesn't participate is nitrate over here on the left. Okay, now that we fix that, we write out the net ionic equation, Ag1 plus aqueous plus chloride 1 minus aqueous goes to form silver chloride, the insoluble product. Falls out of solution. So those are the three kinds of equations. And this up here shows you, the two solutions you're mixing together, and what you get is a solid precipitate, which I abbreviate normally as PPT, and an insoluble precipitate and the soluble salt that stays behind in solution. Down here you write down the full ionic equation, number 2, so 1, 2, and 3. The second equation lets you identify your spectator ions so that you can remove them and come up with the net ionic equation, which is a lot simpler to write out and doesn't leave you scrambling to try and take into account things that just don't matter. The sodium and the nitrate up in the first equation. They don't participate, we don't need to consider them, but the first equation, you kind of have to. The third equation only has the stuff that's participating, only has the stuff that matters. We very rarely use the second equation for anything. It doesn't help us to do much. Its main function is just to help you get from 1 to 3. It's just a lot of extra writing for an equation we're not really going to use for much. Let us move on from talking about soluble compounds in general to talk about a specific class of soluble compounds. Acids and bases. Acids and bases are a class, or a broad category, two broad categories I should say, of soluble compounds that are highly reactive. And they are reactive in particular ways. Okay. There have been multiple definitions of acids and bases through history, and we have them listed here from the narrowest definition to the broadest definition. Not by coincidence, this is also the oldest definition to the youngest definition. The first was proposed by a dude who went by the name of Arrhenius, and he defined an acid as anything that donates a proton, an H+, into a chemical reaction or a dissolution, and a base as anything that donates a hydroxide, an OH-. Okay. In other words, according to the Arrhenius definition, okay, hydrochloric acid is an acid because it splits apart into H+ and Cl-. The HCl is donating the proton into solution, and that's what makes it an acid. And on the other side, you have sodium hydroxide, or Li. You throw it into solution, it breaks apart into Na+, and OH minus. The sodium hydroxide is donating the hydroxide into solution, and that's what makes it a base. This is a good definition, and it covers the majority of acids and bases out there, something like 95%. Okay? It's a great definition. Problem is that it ignores some things that are clearly acids or bases. I mean, they react exactly like acids and bases do, but they don't match the Arrhenius definition. So, for example, NH3, ammonia. It is a base, but it doesn't donate an OH minus into solution. Okay? There's no OH minus. There's no secret hidden hydroxide in ammonia. Okay? It's not like you pick it up and shake it and hydroxide falls out. No, it doesn't do that. But nevertheless, ammonia is a base by any measure you care to make, which brings us to the second definition. This is the one you'll see even more often than Arrhenius. It's the Bronsted-Lowry definition, which I like because it has that awesome O in the middle of Bronsted's name. I don't know how that changes the pronunciation of his name, but I like it, so I always include it. Okay. Now, according to the BL definition, an acid is anything that donates a proton. A base is anything that accepts a proton, or an H+. Okay. So that changes things quite a bit. Okay. So, Bronsted-Lowry, hydrochloric acid is still an acid in the exact same way because it donates a proton. Okay. But now, NaOH isn't really a base anymore. Instead, it splits apart into sodium and hydroxide. And now, hydroxide is a base because it is a proton acceptor. Okay. Meaning that OH minus plus H plus yields water. Or to put it another way, the Bronsted-Lowry definition is an acid is anything that that donates a proton. A base is anything that reacts with an acid. So it makes it less awesome when you put it that way. But now it explains why ammonia is a base. Because you throw ammonia into water, it will react with the water to make NH4 plus OH minus. In other words, base that turns water, sort of, into an acid. Because now H2O, not A, OH, H2O is donating a proton to ammonia. So, ammonia is acting as a base, water is acting as an acid to produce ammonium and hydroxide. And that's why, as I've said before, you'll often see ammonia and ammonium hydroxide sort of treated as synonymous. Because you throw ammonia into water, you'll get a reaction that produces ammonium hydroxide. It's actually an equilibrium reaction. Speaking of equilibria, remember equilibria is just the plural of equilibrium. And speaking of equilibria, that gives us something else we can consider. I'm going to go ahead and introduce you to the term now. So if you have an acid reacting with a base, you'll get a reaction like this. A minus plus, or A plus, nope, that's A. I had it right the first time. A minus plus BH. Let's try and be consistent here. HB plus. Okay? And this reaction, it goes both ways. It's an equilibrium. Okay? Meaning that over here on the left, you have an acid and you have a base. But over here on the right, notice that going in the other direction, when you write it out, you have BH plus A minus going to form B plus HA. In other words, BH plus is donating the proton back to A minus, which means that A minus is a base, and Hb plus is an acid. We'll get into this more later, but A minus is the conjugate base of HA, and Hb plus is the conjugate acid of B. And sometimes the conjugate base is a good base, sometimes it's not. It depends on what compounds you're looking at. But for example, if you throw NH3, a nice weak base, into solution with HC2H3O2, okay, this is ammonia, and this is acetic acid. They will react to form NH4 plus and C2H3O2 minus. In other words, ammonium acetate. And in this situation, ammonia is a base, acetic acid is an acid, ammonium is the conjugate acid of ammonia, and the acetate anion would be the conjugate base of acetic acid. So again, this is the sort of thing that's going to come up a lot more later. I just wanted to go ahead and introduce it to you now because it makes sense in the context of Bronsted-Lowry acids and bases. It did not make any sense in the context of Arrhenius acids and bases. And once again, we've hit the 15-minute mark, so we'll go ahead and call it quits there. And next time we'll come back, we'll finish talking about the different definitions of acids and bases before moving on to a little bit of work with acids and bases.